Synchroton light source here in Campinas, which is almost 10 times as big as the one we already have. This new one is called the CCES project, and it has a 165 meter diameter. This one, I think it's a 30 meter diameter. And the requirement for it to operate effectively is that it needs to vibrate around 10 to minus 6, so a micrometer. And this massive concrete foundation needs to vibrate like in the orders of micrometer in order for it to work. So the question here is, how do you design a foundation that can vibrate so little, right? Since you can, like, buildings like this vibrate to an extent that we can actually feel it. So the project here, so this is the most used construction technique for foundations of a synchrotron light source. This example here is the diamond light source in the UK. You can see that it's made, the foundation is made up of a large group of piles. It's a bunch of piles like this. This is a 2D scheme of the foundation. It has a large group of piles, and the piles hold this large raft foundation made of concrete. And this whole group, the whole group of raft foundation plus the piles interact with the soil in a way that's very complicated to understand and to model. So the goal of the project here is we can divide the goal into 3 parts. The first one is the determination of the soil profile. You can do measurements in the soil where the foundation is going to be built, and you can understand if the soil, what's the porosity, what's the permeability, and things like that. The last part is together with what we know of foundations, then we can see what's the best construction that for that particular soil profile that can minimize the vibration levels of the foundation. And in the middle here is the determination of the soil foundation response, so we can see which one of those foundations can be used for the design part later on. In this part here, we divided the part of modeling the foundation in 3 different parts. We divided it into the study of plates, the study of piles, and the study of wave propagation. We need to understand how plates interact with the soil because the synchrotron light source is built as a raft foundation supported by a group of piles, right? So the second part is to understand how piles interact with the soil. And what I wrote here as wave propagation is other mitigation techniques that we can use, such as trenches and barriers around the foundation, so as to minimize vibrations that come from the outside and hit the foundation. So the project here is divided into modeling and understanding how plates interact with the soil and how piles interact with the soil, and how we can come up with a model that involves those 2 foundations together, so we can model a raft foundation that's supported by a large group of piles and interacts with the soil. And then later on, determine what's the construction techniques, how many piles or how deep they must be in order to minimize and satisfy the vibration requirements of the foundation. So I'm going to illustrate a technique that we use here using beams and bars, because I'm pretty sure everyone's more familiar with beams and bars than with plates and piles. The technique is based on a Lagrangian approach in which we determine the energy, strain energy and kinetic energy of all the pieces of foundations together. And then we come up with an equation of motion that describes the problem based on those energy terms. And I'll illustrate this first with the case of a beam. Everyone is familiar with the case of a beam. This is a one-dimensional elastic beam. This is the differential equation that describes a beam problem. And we want to determine this displacement here, the deflection of the beam in the y direction here. So we don't know the solution of this differential equation, but we can come up with a trial function and say that I don't know the displacement of the beam, but I can say it's made up of a bunch of terms, exponential terms multiplied by generalized coordinates that we don't know a priori. This graphic here illustrates each of these exponential terms here. So when n equals to 0, we have the blue curve. When n equals to 1, we have this curves here. So if you multiply each of these curves here, each of these curves is the exponential for different values of n. If you multiply this by the appropriate generalized coordinates, then we can arrive at the actual deflection of the beam. So this is just to illustrate. I multiply these exponential terms by a bunch of random generalized coordinates. We come up with this curve. So you can see that if you adjust the generalized coordinates accordingly, then you can come up with the actual deflection profile of the plate. So this doesn't satisfy this particular beam, sorry, I said plate. This deflection profile doesn't actually satisfy this beam problem because we know that it doesn't satisfy the boundary conditions here. For this particular beam, the deflection in 0 and L is 0. In this case, it's not 0. So this is just to illustrate that how we can combine these terms here to come up with any deflection profile. So the challenge here is not anymore to solve this differential equation, but to solve the generalized coordinates that satisfy the deflection profile of the beam, right? So one thing that we can do from here, since we have the deflection profile based on this form, we can derive it with respect to time, with respect to the space one time, with respect to the space 2 times. And this is the expression of the moment, and this is the expression of the rotation of the beam. So we can incorporate, for example, boundary conditions based on rotation and moment and then so forth. Another thing, we can determine the kinetic energy of the beam. The kinetic energy is simply the mass multiplied by the square of the velocity. So I showed you that we have the velocity here in terms of the generalized coordinates. Then this is the expression for the kinetic energy along the body of this beam. And after substituting this expression here, after a lot of manipulation, we can come up with this expression. Or more simply, you can write a matrix equation for this, in which M is given here. It's a very simple equation. It involves geometric properties of the beam and also the mass density of it. And then analogously, we have the strain energy is written in this form, matrix form, in which this matrix K is this expression over here. And the last term of energy that we have in this problem is the potential energy of the external loads. In this case, it's a uniformly distributed load. So the potential energy of the beam is given in this form here. So you can see that the final expression is a very convenient matrix form and involves the generalized coordinates, alphas, that I don't know the value of them for a particular problem. We can
it's just the weight, the potential, the external load is just the weight of the beam itself.
Yeah, you can see this as the weight, but you could also include here any other expression for loading, right? So we combine all of these. Also the boundary conditions can be written very easily from the trial function that I showed you. We can say the displacement in 0 here and in L are 0. The moment in 0 and L are also 0. And then you can combine this expression also in this matrix form, very convenient. It involves the generalized coordinates. And then we include all of this in the Lagrangian of the problem that involves the kinetic energy, the strain energy, and the potential energy of the external loads. But this Lagrangian doesn't satisfy that particular beam problem because it doesn't incorporate the boundary conditions, right? So we can incorporate here the boundary conditions multiplied by a set of Lagrangian multipliers that we also don't know the value of. And then the equation of motion for that beam problem can be determined from this expression by deriving the Lagrangian of the problem according to the alphas, the generalized coordinates, and deriving the two according to with respect to the Lagrangian multipliers. And then at the end, you have the equation of motion that, because we put all of that in the neat matrix form, we can come up with this final equation that's in matrix form. And then this is all known. This matrix involves the matrix M and K from the kinetic and strain energy that I showed before. The B is the matrix from the boundary conditions. The F corresponds to the loading. So this is all known except for the alpha and the Lagrangian multipliers, right? So if you solve this equation here, you will arrive at the generalized coordinates that you plug back into the trial function, and then you have the actual displacement of the beam.
That one is the secular equation? It's called secular equation?
Which one?
This equation here is called a secular equation?
Is it? This one?
I'm asking.
This is the equation of motion. And
No, the equation number 16.
16? This one?
Yeah.
I don't know. Is there a name for it?
No,
I don't know.
looks up.
It's a secular equation.
Mhm.
Right now?
So this is an example for one particular beam problem with these data. This is area, moment of inertia, the Young's modulus, the length, and the intensity of the distributed load, and the mass density. We have an analytical solution for this particular beam problem. You can see that it matches exactly our solution here. This is a comparison with the FRF, comparing with ANSYS, which is a software of finite elements. You can see it also matches exactly for this particular parameter set. And then we did the same for a case of a bar. The difference in here that the differential equation is simpler, but also we can come up with a Torah function for the solution of that differential equation.
Get back a little bit.
Yeah.
I think I missed something. So you saw that this is
Yes. Yeah.
So on the right is the static problem.
This is the This
alpha
is
dot is
oh,
derivatives of the alphas is just the static.
this, yeah.
Okay, what is analytical and what is present?
The present is the solution with this method that I just showed you, and analytical is just solving the beam by hand. This is the deflection profile along the body of the beam. So you see from 0 to 10, that's, oops, this is wrong. This is 0 to 4, I guess. Hmm? And the other one is the FRF, the frequency response function of a certain point of the beam. I took the displacement at 1/5 of the length, so around here, a point around here. So we have for different values of the frequency of excitation frequency of the external loads. So I have the external load is intensity 1, but with a frequency of 2 hertz, and then 4 hertz, and then 6 hertz. So we have along for different dynamic loadings, then we have this point over here displaces with this amplitude, and then this amplitude, and so forth.
Those spikes are resonance?
Yeah.
Vibration?
Yeah. Yeah, so it has resonance over here around like 1 something, and 4 like 5 something. Mm-hmm. Sorry, I went too fast. So the same technique was applied for the case of a bar, and then for the bar we established this trial function exactly the same. So we have a bunch of exponential functions, and then we multiply by beta, generalized coordinates that we don't know the value. And then if you determine the strain energy of the bar, the kinetic energy, and for this case we don't have external loads, but we apply external displacement. You also have the potential energy for that. And then if you solve the final equation that's exactly the same for the beam, then we arrive at the betas here. And then this is a comparison for the displacement of the top of the beam, the displacement of this point here, for different values of delta 0, so it matches the analytical solution. This is also the frequency response for a certain point of the body of the bar, just 3/5 of L, this around here, point around here, for different frequencies of the delta 0. So you apply a displacement with different frequencies.
Again, and here you have also gravity on the vertical.
No, this case, the only excitation that's applied is the delta 0. It's a displacement, prescribed displacement at the tip of the bar.
But in the other case,
The other case,
horizontal, you have a equally distributed
yes,
load.
yeah.
And now here, how it is.
And here you have only this load. It's a prescribed displacement at the tip of the bar.
But you don't have the bar is not sufficiently low so that the...
No, there's no load at all. There's no load at all along the body here. You could also include the weight of the bar or other kinds of loading, but in this case, I'm just applying a displacement at the tip. There's no weight. And then what you can do, because we're using a Lagrangian approach, the beauty of this approach is that because it's all linear, we can solve a problem that incorporates lots of different elastic bodies by simply adding the energy to each of them. So the final Lagrangian for this frame problem here includes the kinetic and strain energy of the bar and of the beam, and then the potential energy of the external loads in here. And then the Lagrangian, the final equation is just as simple. So that's the convenient part of it. The difference here is that we have for the a trial displacement for the beam, the part that's on top, a trial displacement for the bar, the part that's in the bottom. And we also apply the boundary conditions here at this point to this point. And in addition, to say that this bar and this beam are actually together, we also have to say that the displacement at the middle of the beam is equals the displacement at the top of the bar in here. That's what establishes that they are actually like one frame problem. And this is made like this. We say that the displacement of the top end of the bar equals the displacement of the middle of the beam. And then you just have like an additional line in the boundary conditions matrix. Yeah. So here we also have a few examples for the frame problem. This is the displacement of the beam part of it. You can see that it changes a bit, and then this part here corresponds to the displacement at the tip of the bar. This is the frequency response for a point over here. This point over here for different values of frequency. And here I'm also showing the elastic solution, which means that the bar and the beam don't have any damping factor associated with them. They're purely elastic. So you have these resonances over here and here. But in this model, we can also incorporate easily a damping factor in the body of the frame. And it also matches, these are our comparisons with ANSYS, with the finite element solution. So you can see that it also matches exactly even for damped cases.
So that means that in a 10-meter bar, the form is just 1 millimeter or 4 millimeters, the first graph.
Yeah. Mm-hmm. Yeah, these are not real. It's just like I didn't choose the data very well, so I guess this might be too much for the particular Young's modulus that I gave. But this is not a real problem, but the solution matches the analytical solution anyway.
What, I didn't understand this question.
No, he was just asking about the magnitude of the displacement here.
But it's multiplied by 10 to minus 3, right?
Yeah. So it's like 4 millimeters and 10 meters of the beam. Now, how do we apply this technique for the actual problems of interest? We want to solve plates and bars like these to incorporate into the foundations later on. So the solution of the plate, the differential equation that describes the plate is actually exactly the same as the one that describes the beam, with a few correction factors to take into account that the plate is actually a circular 3-dimensional problem, and the beam here is actually a 1-dimensional line, right? But for the case of the bar, it's exactly the same differential equation. So the calculation of the strain energy and kinetic energy and the potential energy of the external loads is all the same. The difference.
It's just one coordinate.
Yeah.
Switch that to cylindrical coordinates, just one coordinate will matter, which is the
Yeah,
radius.
because we are working with circular foundations here, you use cylindrical coordinates. So the differential equation is also 1D. So it involves R, the direction of R, right? R. So the difference here is that we need to take into account the effect of the soil, right? Because the plate and the pile are not vibrating like a beam. They're not by themselves. They actually interact with the soil. So the way we do this is that we need to determine what's the external load that's applied on top of the plate is easy to determine. But the thing is, we need to determine the contact load between the plate and the soil. So, and that's the contact load, the traction surface forces is the one that's going to deform the soil, and then we need to determine the strain energy of the soil, which is deformed by those contact tractions. In order to do that, we also don't know the contact tractions, what they are, how they're distributed and everything in the contact surface. But we can also say that they're made up of, we can also establish a trial function for them. and say that they made up of a bunch of generalized coordinates multiplied by a bunch of terms. And these terms, again, we say that the traction in between the plate and the soil is composed of lots of different terms, and one of the terms is responsible for making the plate deform as this curve here. The other term is responsible for making the plate deform as this other term here. And the actual traction that's in there is going to be determined when we find out those generalized coordinates again. So the difference is that we have to incorporate the strain energy of the soil as well in the Lagrangian, but we can also establish a trial function for that contact fraction. So the final equation of motion is also very simple. It's a matrix equation. The only difference is here that we have to incorporate the strain energy of the soil. So here are some results that we've been obtaining. This is this one compares. So the soil is made up of homogeneous rock. It has like some properties there that I didn't show here. And then on top of this rock rests this circular plate. And then we compare what's going to happen if there's like a blizzard or something, and then a layer of ice is deposited on the top of the beam. In the layer of ice, we also know the properties of the ice sheet. So we can compare how the vibration of the plate is going to be affected by the position of the layer of ice. So you can see here, this is the real and imaginary part of the vibration of the plate. It's a point on the middle of the plate. The plate is rigid. So we have the blue curve is without the ice sheet. Here is the imaginary part. And the green curve is the vibration of the plate with ice sheet. So this is one of the things that we can do, but we also can incorporate different kinds of soils. We can consider layered soils. We can consider that the plate is embedded within the soils, and like this problem here, for example. It's a problem of one layer, two layers, right? One layer of ice and one layer of rock, and the plate is actually in the middle of them. So this is one of the things that we can model. The other thing is for the plate, the pile problem. This is a pile that's embedded in a homogeneous soil. I also didn't show the properties here, but I'm showing you the vertical impedance. That's the force that's applied, the center force that's applied divided by the resultant displacement. So this curve shows the real and imaginary part of the vertical impedance of this pile. This is a short pile. The length of it is just 5 times its radius. The mass density of the pile is the same as the surrounding soil, but I consider here in this graph different stiffness of the pile. So the blue curve, it's 10 times stiffer than the soil, up to the purple curve in which it's 1,000 times stiffer than the soil. So we can also determine how the vibration of the pile is affected by different construction properties, right? So the next thing is we actually want to determine the vibration of a group of piles, right? So to model a group of piles, we have to incorporate the strain energy of all of the piles that's involved in the vibration here. But it's simple. We can determine a trial function for the displacement of all of the piles, and we say that the displacement of a pile I is given by this expression here, which is simply like it's the same expression as before, but now we have a set of generalized coordinates for each of the piles. I've implemented this problem here. I've implemented this problem here, and then it's still in. It's a preliminary implementation still, but one of the things that it has to satisfy is a minimum physical consistency test, right? So the first physical consistency test is that if the radius between the piles is very large, because the soil absorbs all the energy that comes from the external load, then if the piles are too far from each other, then they wouldn't notice the presence of the other pile, right? So if the pile is too far, then the response of the pile group will be as if there was only one pile in the soil.
Gas phase approximation of piles.
So this is the test. This is a preliminary result. This is the vertical impedance of 2 piles. There's 2 piles in the middle and the soil. And the distance between them varies from 10 times the radius of a pile to 200 times the radius. The star here is the response of a single pile. And you can see that as you increase the distance between the piles, the results actually tend monotonically to the response of a single pile. But the problem here is that this should happen when the piles are around like 20 times, or actually 10 times the radius distance between each other. And we can see that they're already 200 times the radius apart from each other. They still didn't converge to the response of a single pile. So there's something wrong here in this implementation. I still need to check this. And then the next phase after this, after I have a working solution for a large group of piles, I have to couple them together with the response of the raft foundation that's on top, the response of the plate, right? And to do that is just as I showed you the problem of the frame. It's just additional boundary conditions to account for the fact that they're actually vibrating together. So I have to say that on top of the displacement on top of each of the piles equals the displacement of different points of the raft foundation. And then I solve this whole system together, and then I arrive at the response of the raft foundation supported by a large group of piles. That's going to be the final goal of this project. This postdoctoral project is being funded in part by FEPES, different FEPES projects, and also copies during my PhD, 5 packs Unicamp and CNPq. Thanks for listening.
Just a curiosity, so you're saying that out of the materials and the pieces involved in the foundation of a possible light source, and you're finding what are the best properties those things have to have, right?
Mm-hmm.
I'm wondering, once you find the right parameters there, how easy it is to incorporate those in the real manufacturing of those pieces, and how they can change the manufacturing processes to match what you're predicting.
Mm-hmm. Yeah, this is the third part of the project here, right? How to design a synchrotron light source. It involves these 3 parts. The part that I'm working on is because in order to make these engineering decisions that you're mentioning, we need more information. We don't have models that describe accurately how foundations interact with the soil. We still don't have those. So the work that I'm doing here is in the middle part, is developing our know-how on this thing, or the soil foundation interaction. Later on, with more knowledge on this area, that we know how they interact, and we can actually simulate with different properties, then we can make engineering decisions. That's the third part that you're mentioning here. I still don't know what factors matter the most or don't matter at all.
The height, in the last part, the height of the pile, the ratio of the height to the radius is only 5. Does it matter?
Here?
Yes.
Here?
Yeah. Okay, so then in the other one, where you go to the gas phase approximation of the pile.
Oh, okay, here.
Yes.
Here.
Does it really matter what is does it have higher piles compared to the diameter?
Yeah, it could be, but I think this is more like numerical errors, because the model is very... the soil part of the problem is hard to solve. It's we need to solve like indefinite integrals of decay and oscillating terms with singularities and stuff. So it's a complicated problem to solve. I think this is just like if I refine the integration process of the soil part, and it's going to improve it. But for whatever length of the pile, after a certain distance, the effect of the other one should vanish.
Any further questions? Not then, thank you.
Thank you.